Hi everyone, this is Kirti, and I know there's a lot of content to review for exam 1, so I thought I'd try to put together a little video guide to help out with reviewing some of this content. And if it's useful, I may add on another one to talk about the properties of sound specifically, but this one is more of a review of the basic physics concepts that you'll need to know. So first I wanted to go over this kind of like contrast between different concepts we talked about in this unit. So for example, we have distance versus displacement. And so what is the difference between these two? So let's say I have a little person, and this person is running from here to here, and then goes back here. So let's say he goes 5 meters this direction, 5 meters back this direction, and then ends up in the original spot. So distance will be the length of this direction plus this direction. So distance would be, in this case, 5 plus 5 meters, so it would be 10 meters. But displacement, on the other hand, will be the change in position. So in this case, if this guy starts off in this position and stays in the exact same position, then the displacement is actually what? The displacement would be 0. And so this is where we get introduced to this idea of scalar versus vector measurements. So this is definitely an important concept to know. It's differentiating between scalar versus vector, because scalar measurements, they only contain magnitude, but they contain nothing else. So with distance, all that matters is the magnitude of the length traveled. But with the vector, we have magnitude, so that still exists, but we also have to account for direction. So in this case, because this person ran back in the exact same direction, or in the opposite direction, I should say, that they came from, and then they end up in the same position. So their final position matters for displacement, but it doesn't matter for distance. And we have one more concept that's based on the same contrast, and that would be speed versus velocity. So what we see with speed is that I can say that I'm going this many meters per second. So I'm crossing this many meters in 1 second. So if I cross 5 meters in 1 second, then this would be my speed. But for velocity, that's not enough. Velocity also asks not only what is the distance covered in an amount of time, but what is the direction that the object is traveling in? So velocity is a vector property. And so if I'm going in this direction, I would have to say like it would be 5 meters per second, but specified in this direction, whatever that direction is. And the important thing to note is that it's velocity and not speed that will end up being used for things like acceleration, or generally in a lot of the physics-related equations, you'll see velocity. And one thing that I wanted to note was this relationship between velocity, acceleration, and displacement. And so this is really important to note. This is what I called the VAT formula. And basically this is rooted in the fact that, okay, so we know velocity is equal to displacement over time, okay? And we know this, how we know this, because our unit itself is meters per second. Meter would be a unit of displacement, and then second is a unit of time. So this is our original equation. And then we're trying to define acceleration. So acceleration is going to be the change in velocity over the change in time. And basically, if we rearrange this equation, that's how we get this equation. So we get, this is what I call that BAT equation. That's not a real term, just something that may help you remember. So change in velocity equals acceleration over times time multiplied by time. And when I say change in velocity, what I mean is you take the final velocity and you subtract it by the initial velocity. So for example, if I have this car, ignore how bad this car looks, but I have this car and it starts at rest. So when I say at rest, what does that make my initial velocity? It makes it 0. And then it accelerates to some sort of final velocity. And so that final velocity is going to be, let's say 5 meters per second. We've got to include our units. So then my change in velocity is going to be this final velocity minus the initial. So in this case, 5 minus 0 equals 5. And that shows us our change in velocity. And then basically we can plug in all these factors to determine, one item or another. So for example, if I wanted to solve for acceleration, which is here, and let's say, so my change in velocity is 5. Let's say that the car, it took one second to go from 0 meters per second to 5 meters per second. So that would make my time 1. So then in this case, I would go ahead and divide by 1, that cancels out. And then I'll get that my acceleration equals 5 meters per second squared, because that's the unit for acceleration. So I would know how to use this type of formula. But the two main formulas that you'll need to know is how can I solve for my final velocity? So this is based on this formula right here. So we know that change in velocity is the final minus the initial. And so I'm just kind of rearranging this formula where I get final velocity equals the initial velocity plus acceleration times time. And then the other formula that I'll need to know with that is how to get displacement. So displacement will be, let me make this. So initial velocity is usually, it's also called v naught. So it'll be used like that. And this is how we can get displacement if we have the acceleration and the time. And so these are the two equations that you'll really need to know, and you'll need to know how to use them as well. So let's say, so in this car example, okay, so I said, what terms have I defined so far? Let's see. So I said my v naught, my initial velocity is 0. My final velocity is 5. And so we determined that the acceleration here is going to be 5 meters per second squared. Remember to add our units to everything. And then the time it took was 1 second. So we basically have everything we need to solve for the displacement. So how far did this car change positions from its initial position? Where did it go to? That's supposed to be a question mark. Where did it go? And so basically we can just go ahead and plug this in here. So displacement is going to be, so what is our v naught? It's 0, and the time passed was 1, and then we add it, plus half times our acceleration is 5, and then we have our time, it's 1 squared, which is just 1. And so I'm just gonna keep simplifying that. And then basically we can just get 5 over 2 is 2.5. And the unit for displacement is meters. And so this would be the displacement. So it's changed position by this many meters from the original position. So make sure you know how to use these two formulas here, make sure you know how to use this VAT equation where you can find your final velocity, and then also know how you can find displacement whenever you have your initial velocity, time, and acceleration. So the next thing that I wanted to move on to was different laws of nature, because we did cover a few. So let me say these are our laws that we need to note here. So first we have this law of universal gravitation. It's taking me a while to write this out, but we have the law of universal gravitation. And so basically this is based on Newton's observations, where he's like sitting under the apple tree, right? And Newton sees that the apple falls to earth. So why does the apple fall to earth? So basically the law of universal gravitation says that if there are two objects, let's say this is my apple and this is the earth, and granted the earth is much, much bigger than this apple, the law of universal gravitation says that any object that has a mass to it, or an amount of matter, is going to exert this gravitational force on one another, right? And the bigger, gravitational force, and the bigger the mass of an object is, that means the stronger that gravitational force will be. But the bigger the distance is between the objects, that decreases the gravitational force. And basically, so with the apple example, if I go and I send the apple way out here, I send it all the way to space, and it's not even near the earth, then Earth's gravity will not have that attraction. It will not draw the apple towards the earth. But if it's close to the moon, let's say, the moon would draw the apple. And so we do need to know this idea that gravity is this law of attraction between two objects that have mass. But actually, when I was talking about mass, I wanted to go ahead and give a little review. So what is mass? Mass is the amount of matter that's in an object. And this is measured in kilograms or grams, something of that nature. And mass is one of those properties that it does not change. So my mass on the moon would be the same as my mass on Earth. It doesn't matter. But when we go to, I was talking about these different contrasts here. And so just like we have all these other concepts that contrast, we're also going to have this contrast of mass versus weight. So, sorry, I'm switching up a lot here. So we have mass versus weight. And this is where this law of gravitation comes into play, because basically weight is something that changes. So my weight on the moon will not be the same as my weight on Earth. And why is that? It's because of the gravitational force. And so basically weight is a force. Okay? So weight is a force. And basically weight accounts for not only the mass of an object, but also the mass of its acceleration due to gravity. So this item here will be acceleration due to gravity. So that is something that's important to know. And I'll talk more about, actually I can go ahead and talk about force now. So this goes to what I call, I don't know why I just give nicknames to these equations. I think it just helps to remember it. So basically this is the FAM equation that says that force equals our acceleration times mass. So we have acceleration and we have mass, and or you could say force equals mass times acceleration. Doesn't matter, whatever helps you remember it. So in this case, you can clearly see that weight is a force because we're taking our mass into account, but then we also take into account acceleration. In this case, it's acceleration due to gravity. Yeah, I think that's about it for that part. So let's keep continuing. So we have our law 1, which is universal gravitation, and then we also have the law of inertia. And this is another one of Newton's laws. So the law of inertia basically says that an object in motion tends to stay in motion, and an object at rest tends to stay at rest. So basically that's telling me that any object with mass will resist change, okay? Will resist change in either their state of motion or their state of rest. That's about all you would need to know for the law of inertia. The other thing I saw in the study guide, it also mentioned something called Hooke's law. So basically, Hooke's law has to do with elasticity. So I would put that as like a key word here. It has to do with elasticity. Okay, and basically it's saying that let's say you have some object that has elastic properties. So I guess the easiest example would be a spring. And we know that with a spring you can either stretch it or you can compress it, right? So you can bring the spring together. This would be compressing it. Or you can stretch it out even further. This is supposed to be stretched, so this would be stretching it. And all that Hooke's law really tells you that you need to know for now is that the force that's required to either compress the spring or to stretch the spring is going to be proportional to the displacement from equilibrium. So for example, if I only stretch the spring by 1 meter, right? It's going to take a certain amount of force to do that. So let's say the amount of force equals F. But by contrast, if I decide to stretch it 2 meters, and let me make the stretched part a different color here. If I decide to make it 2 meters, then basically my force is going to be 2 times F. And you don't need to know the details, but just know the more you stretch or compress something, the bigger that displacement is, the bigger the force is as well. And also there's going to be something called the restoring force that brings that spring back to its original place. So after that, so we do have something else another law that we'll talk about, and that'll tie us into our final few topics for this basic physics concept. And we have something called the law of conservation of energy. And this one, it sounds really elaborate, but it's actually one of the more simple laws. And basically what it says that energy is only changed, but it's never created or destroyed. Never created, and it's never destroyed. And so basically what that means is that energy will change from different forms. So there are different forms of energy. And we talk about it a little bit later. We have kinetic energy, we have potential energy, we have thermal energy. So we have a lot of different types of energy, and energy will change from one form to another, but it's never created, it's never destroyed. You're never going to lose energy, well, you're never going to destroy or, like the energy won't just disappear. It's always going to be somewhere in that system in some form. I guess the common example is like if I'm holding a ball, so I have this ball, it has potential energy right here when I'm just holding it. But then when I drop the ball, it changes into kinetic energy, which is basically the energy of motion. And you don't need to know that, but it's just an example to say that the energy is never lost. It's just converted from one form to another. So speaking of energy, what is energy? So this is going to be this relationship of work, energy, and power. Let me actually start with work first. So work is basically going to be force exerted over some displacement. Let's say over displacement. And so my example would be if I'm pushing this box, I have this box here, and I want to push it over this displacement. So in order to do that, I apply a force, right? And so in this whole action, I'm doing work. And basically work causes a change in energy. So it's causing a change in energy, okay? Basically the energy is being transferred from one object to another. So if I have this energy, right, then basically I am going to use this energy in some way, and this energy is being changed. For example, like potential energy is changed into kinetic energy, and that energy is what allows this work to take place, basically. So the unit for this will be the joule. It's the same unit as energy because it's basically just a change in energy. And then what is energy? Well, we can kind of define it the other way, where energy is basically the ability to do work. And it's kind of abstract, but that's the root definition. So again, energy can be changed in many ways, but never created or destroyed. And energy can be transferred between objects. Like energy can do so many things, but just remember that energy is never created or destroyed. And then finally we have power in this little trio of concepts. And basically power is the rate of, well, there are two options here. It's either the rate of work that's being done, or it's the rate of energy being transferred. And that's about all you need to know. I would keep in mind the unit. So for work, it's the joule. For energy, it's also the joule. So this is spelled like this, the joule. And then for power, it's a little different. It's the watt. So we can think of like watts of electricity or something. And then speaking of all these ideas, we have work, energy, power, force, so many different things at play. So then we'll talk about pressure, and then we'll talk about intensity. So actually, let me talk about intensity first. So we have this idea called intensity. And basically, intensity is the amount of power that we exert over an area. Okay? And so for example, if the sun's rays, right? So we have our sun, and it's shining all these rays to the earth with the same amount of power. So here's our earth. So if there is this really large area, so this is a large area, I'm gonna make this capital A, that actually means that there's a smaller intensity. The same amount of power, so the same amount of power, but it's a smaller area. Or sorry, this is a larger area. It's the same amount of power, but then it's distributed across this larger area. But let's say the sun is feeling very angry that day, and it gives this tiny concentrated stream, and it's only doing a really small area, but it's the same amount of power. So if it's the same amount of power and it's less area, you'll see higher intensity. So that's basically what you need to know about intensity. And then, and you can see we're making this transition into the properties of sound. We talked about pressure. And pressure is going to be really important, especially when we think about air pressure. Basically, pressure is the amount of force exerted over some sort of area or volume. And basically, this is where we get into, to add on to our list of laws, I'm going to go ahead and add Boyle's law, which you already probably saw on the study guide. I'm just going to add that in here. So we have Boyle's law. And all Boyle's law is saying is that basically as the area increases, if force stays the same, so let's assume if force stays the same, and there's also this other caveat if like thermal energy stays the same, so the heat, everything, all that stuff is the same. But the area increases. What does that mean? That means the pressure decreases. Okay? And so, for example, if I poke you with a needle, okay, so the needle has a really, really small area. So what does that mean for the pressure? That means the pressure is going to be really high. And that's exactly why a needle is able to puncture skin. But then if I were to poke you with my finger instead, we have a larger area, and therefore the pressure decreases, and I'm not able to poke through the skin with just my finger, you know? And so this is all assuming that force has stayed the same. So keep that in mind. So pressure can either be increased by force. So if there's an increase in force, there's an increase in pressure. But if there's an increase in area, there's a decrease in pressure. So just remember that relationship is what we call Boyle's law. And basically, this is important when we think about breathing. You know, we've started the respiratory system. So if we have our, I know I'm going to draw this so badly, but we have our lungs, right? And as our lungs expand, what we see is that the volume increases. So not area, but volume. But kind of the same idea here. So instead of area, we could also say that it's kind of like a, not that this is the equation, but area and volume are very interrelated, right? So if we say force stays the same, and then the volume increases. So when the volume increases, the pressure, as you can guess, will decrease. So when our lungs expand, that's going to increase the volume, and thus it decreases the pressure within the lungs. And so let's see if there's anything else. Honestly, I would just like talk about these. So we have these molecules, right? So let's say these are air molecules. And these molecules are moving really, really randomly, right? And why do they move randomly? It's because of what we call Brownian motion. So let's say why is it moving randomly? Brownian motion. And you don't need to know a lot about this, except that Brownian motion is what causes this random movement. So when you think of Brownian, you should automatically be thinking, okay, this is random, some type of random movement. And basically, this is ultimately caused by thermal energy, but you won't really need to know that. Yeah, I think that's about it. I guess one thing to remember is that these molecules will usually, so they're moving randomly during Brownian motion, but usually they'll move from an area with high pressure to an area with low pressure. So if I have this jar, right, and let's say I've been compressing this water. So I have these water molecules and they're really, really tightly kind of like smushed together. So this is a really high pressure environment, right? And then I have this area, and I'm not smushing it at all. It's just kind of this empty container. And then I make a little tube from here to here. What we'll see is that the water is going to want to move to this area of low pressure. So this is another, I guess, aspect to know about the movement of molecules. Now for basic physics, I think this is all I really wanted to review for now. But again, if you guys want a review on the more like sound related or wave properties, then I can follow up with a review video on that. But yeah, that's it for now. Thank you so much.